Today we're going to talk about related rates. These are rates of things that are changing that are related to one another. For example, if you're blowing air into a balloon, then a lot of things are changing. The more air you put in there, the more volume of air you have inside the balloon, the more surface area of the rubber outside the balloon, and the larger the radius of that sphere is going to be. So those rates are all changing. They're all related, but they're all different. When you do a related rates problem, you're going to want to follow a step process. The first thing you definitely want to do is draw a picture, if you can. If a picture makes sense, draw a picture so you can see what's going on. It may end up helping you solve. Then you want to determine what you know. Is the information that's given to you? Do you know this rate is changing at this thing or what? What do you know? Figure out what is it that you're looking for. What do you want to know? And then you need to find some given relationship between what you know and what you don't know and what you want to know and come up with some sort of an equation that kind of relates them all together. And then you want to solve it and, of course, make sure you're answering the question. So we'll start off with a simplistic example. If you know that x and y are differentiable functions of t, that means you can take the derivative of x with respect to t and that you can take the derivative of y with respect to t. And that we know x and y are related in that x squared plus y squared is equal to 25. Let's find dy dt, the rate at which y is changing with respect to t, when we know that x is 3, y is 4, and that dx dt, the rate at which x is changing with respect to t, is 8. So we'll start with that given relationship that we had, x squared plus y squared equals 25. Now notice I'm trying to find the rate at which y is changing with respect to t, and I know the rate at which x is changing with respect to t, so that tells us we're going to differentiate with respect to t. This is where our implicit differentiation is going to come in. So I need to take the derivative of x squared with respect to t, which means I get my 2x dx dt. The derivative of y squared with respect to t is 2y dy dt, and the derivative of 25 with respect to any variable is going to be 0. And so we're trying to find dy dt, so we'll solve for dy dt. We'll subtract that 2x dx dt from both sides, then divide both sides by 2y. Notice these 2's are going to cancel, and we have that the rate at which y is changing with respect to t is negative the x value times dx dt all over y. So we wanted to find this when x was 3, dx dt was 8, and y was 4, which tells us the rate at which y is changing with respect to t is negative 6. So this means that y is decreasing at a rate of 6, whatever the units are. They weren't given because this isn't an actual application problem. Let's give an application problem. So the radius of a circle is increasing at a rate of 10 centimeters per second. How fast is the area increasing the instant when the radius has reached 5 centimeters? This could be something like if you drop a pebble in water, you get a circular ripple, and that ripple is getting bigger and bigger and bigger and bigger. So we'll start by drawing a picture. We've got a small circle that is increasing. This radius is getting bigger and bigger. As you can see, the area of this circle is a lot smaller than the area of that circle, so the area is changing as well. So we know that the rate at which the radius is changing with respect to time was 10 centimeters per second. We want to know the rate at which the area is changing with respect to time when the radius is 5 centimeters. All right, so now we have to find some given relationship. How are A and R related? Well, the area of a circle is pi r squared. And so we're looking at the rate at which A and R are changing with respect to time, so we will take the derivative with respect to t of both sides. The derivative of A is 1, but since we're differentiating A with respect to t, we need a dA dt. Pi is a constant, so I pulled that out. The derivative of r squared is 2r, but with respect to t, we tack on this dr dt. Now, dA dt is what we want, so we'll solve this for dA dt. And we get that dA dt is 2 pi r dr dt. And so now we're ready to say, okay, I want dA dt when r was 5, and we knew that dr dt was 10. So I'm going to throw some units in here. 2 and pi are just 2 and pi. The r was measured in 5 centimeters, and dr dt was 10 centimeters per second. So when I put this all together and I take my 2 times pi times 5 times 10 and my centimeters times centimeters squared, I get that dA dt is 100 pi centimeters squared per second. Well, this should make sense to you because area is two-dimensional and it is measured by square units like centimeters square. So because this is positive, we can say the area of the circle is increasing at a rate of 100 pi centimeters squared per second. Let's take a look at another example. Air is being pumped into a spherical balloon, so its volume is increasing at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the radius has hit 25 centimeters? So we're blowing air into this balloon. The balloon's getting bigger and bigger and bigger and bigger, and I want to know at what rate is the radius changing when the radius has hit 25 centimeters, knowing that the volume is changing at 100 cubic centimeters per second. So we know the rate dV dt, the volume is changing at 100 cubic centimeters per second. I want dr dt specifically when r is 25 centimeters. So how are volume and radius of a sphere related? Well, the volume of a sphere is 4/3 pi r cubed. And I'm looking at the rate at which all of that is changing with respect to time, so I will differentiate both sides with respect to t. The derivative of v is 1. With respect to t, we need that dv dt. The 4/3 and the pi are constants. I can pull them out. And the derivative of r cubed is 3r squared, but we'll need to tack on that dr dt because we're differentiating with respect to t. Notice we want dr dt, so this is what we're going to have to solve for here. Now first, notice this 3 and this 3 are going to cancel. So we have that dv dt is 4 pi r squared dr dt. And dr dt is what we're trying to solve for, so we'll divide both sides by that 4 pi r squared, and we get that dr dt is dv dt divided by 4 pi r squared. Remember, dv dt was 100 cubic centimeters per second. We have this 4 pi, and then we're doing this when my r is 25 centimeters, and I'm squaring it. So not only am I squaring the 25, but I'm squaring the centimeters too. So when I do that, I have 100 divided by 4 times 25 times 25, which gives me 1/25. There should be a pi here. I'm sorry, I messed up and forgot this pi. And then centimeters squared per second, and this turns out to be centimeters squared, so that will reduce to centimeters per second. So the radius of the balloon is increasing at a rate of 1/25 pi centimeters per second. A 5-foot ladder starts to slide down a wall at a rate of 3 feet per minute. How fast is the base of the ladder moving when the top of the ladder has slipped 4 feet down the wall? So again, whenever possible, draw a picture. So here we've got our wall, we've got our ladder, and we've got the ground. Now as this is coming down here, the length of the ladder isn't changing. So the ladder is going to remain 5 feet no matter what. All right, so what do we want? Well, what do we know? We know that dy dt, the rate at which it's going down. Now, because it's going down, we make it negative. Dy dt is negative 3 feet per minute. We want dx dt, the rate at which this is moving away from the wall here. And we want that when y is 4, when we are 4 feet from the top of the ground. How are these related? Well, notice we have this really nice right triangle. And so we have the Pythagorean theorem that x squared plus y squared is going to equal 5 squared. And I want the rate at which everything is changing with respect to time, so I'll differentiate both sides with respect to t. The derivative of x squared is 2x dx dt. The derivative of y squared with respect to t is 2y dy dt. And the derivative of 25 with respect to t is 0. So now I'm looking for dx dt, so I will solve this for dx dt. Subtract that 2y dy dt and divide by 2x. Notice these 2's will cancel. And so I have that dx dt is negative y dy dt all over x. And so I wanted this when y was equal to 4, and I knew that dy dt was equal to negative 3. But what's the problem here? We don't know what x is. But we're trying to do this when y is 4, and we know that x squared plus y squared equals 5 squared from the Pythagorean theorem, so we can find x when y is 4. X squared plus 4 squared is 25, so x squared plus 16 is 25, or that x squared is 9. Now, when we take this next step, when we take the square root to solve, remember, when you take a square root to solve, you have to take plus or minus. But because these are lengths, these are distances, we're only concerned about the positive, so x would be a positive 3. And so now we can see that dx dt is going to be 4. So the base of the ladder is moving away from the wall at a rate of 4 feet per minute. Let's take a look at another example. Two cars leave a house at the same time. One travels due north at a speed of 60 miles per hour, and the other car goes due west at a speed of 45 miles per hour. After 2 hours, what speed are the two cars moving apart? This is definitely a case where we are going to want to draw a picture. So we've got our house here. This car is going due north. This car is going due west. And as they go further and further and further away, the distance between them diagonally is getting farther and farther apart. And I'm looking at for what the rate at which this is changing. So I'm looking for this rate at which this A being how far apart they are, is changing. So we know that dn dt, the rate at which this car is moving, is 60 miles per hour. And we know dw dt, the rate at which this car is going, is 45 miles per hour. And I want to know dA dt when it has been 2 hours. So how is this all related? Well, if you're going due north and due west, you're forming this nice right angle right here. So just like the last problem, we have this nice Pythagorean theorem, w squared plus n squared equals a squared. And so now I'm going to differentiate with respect to t. I want to know the rate at which these are changing with respect to time. So if I differentiate both sides with respect to t, I get 2w dw dt plus 2n dn dt equals 2a dA dt. And so what I'm actually looking for is dA dt, so I will solve this whole thing for dA dt. Great, but if you look back on this last slide, I want dA dt when t is equal to 2 hours. Notice here, I know dw dt and dn dt, but I don't know n, and I don't know w, and I don't know a. But I do know that the car going west has been driving at 45 miles an hour for 2 hours, so how far have they gone? Twice that, 90 miles. And the car going due north was going 60 miles an hour for 2 hours, which means they've been going 120 miles. And notice again, this formed this really nice right triangle where a squared plus b squared equals c squared with the Pythagorean theorem. So after 2 hours, w is 90, n is 120, so we can use the Pythagorean theorem to find their diagonal distance a from each other. And when we do this, again, when we go to take the square root of both sides, ordinarily we would take plus or minus, but because these two cars are a distance apart and distances are always positive, then a is just going to be the positive 150. And so now I've got w, which is 90, dw dt, which was 45, n, which is 120, dn dt, which was 60 miles an hour, all over 2 times a I now know is 150. So now I can substitute all of that in, and I get that dA dt turns out to be 75. So the two cars are moving apart from each other at 75 miles per hour. All right, that's it for now. We'll reconvene in a little bit with some more examples.